Dobro večer svima. Posebna zahvalnost profesoru Andrewu što je odvojio vreme da podeli sa nama svoja iskustva i ogromno znanje. Zahvaljujem se SUZI-u na želji da pomogne svima nama da se ljudi koji se bave ovom oblasti okupe i da podele svoje znanje i iskustva, i zahvaljujem Arhitektonskom fakultetu koji je omogućio da i organizovao ovo večerašnje predavanje. Ovo je jedno u nizu predavanja i SUZI nastavlja sa svojom misijom da pomogne u boljem razumevanju svih problema vezanih za zemljotrese. Professor Andrew, thank you so much because you want to share with us your knowledge and your experience. We are ready to wait you.
Thank you very much, Rade. That's I couldn't understand your introduction, but I'm sure it was entirely appropriate and probably a bit flattering. I'll share my screen. So just checking, can everybody see my shared screen?
Yes, Andrew, everything is okay. Thank you.
Oh, okay. Well, hello, participants. I'm really pleased to be able to speak at this event organized by SUZI. And I hope that you will appreciate, what I'm able to share today. This presentation is primarily designed for architects and architectural students, but I think that professional engineers will also, find it useful, not so much because of any technical information, which I obviously limit because I'm speaking to architects, but because of the overview of the damage to masonry buildings. So with that very brief introduction, I will just get straight into my presentation and start by outlining to you some of the damage to masonry buildings during the Christchurch earthquake in 2011. It was a magnitude 7.1 quake, and it was relatively shallow, I think only between 10 and 15 kilometers below the ground. And so it produced quite intense shaking over a small area, namely the central business district of Christchurch. And so in Christchurch, there was a very large amount of damage to unreinforced masonry buildings. The Christchurch City Council had not taken a very strong lead on requiring building owners to strengthen buildings like these. And I think that can be understood because a lot of these buildings were quite old and the economy wasn't in great shape. And the building owners would have had difficulty justifying the cost of earthquake strengthening. But when this earthquake occurred, it had incredibly severe consequences on almost every masonry building in Christchurch. And most of the masonry buildings experienced partial collapse. So unfortunately, Christchurch has lost a lot of its historic buildings. And here is an example of an old 3-story masonry building in Christchurch. And you can see that most of the damage to this building has occurred by the walls and the gables failing in what we call face load. If I can just explain using this, imagine this little pad is a wall, then the face loads are acting at right angles to the length of the wall. So these are the inertia forces we call face loads. And where walls are not tied into the floors or the roof diaphragms, where the tie along these lines is poor, then in the earthquake shaking, the masonry is incredibly vulnerable to falling out of plane. And so this is a good example, and there would be hundreds of masonry buildings where especially the upper walls just collapsed and fell onto the street. The lower walls are less vulnerable because they experience the compression of the masonry above them. And that compression gives a considerable degree of extra strength to these walls against out of plane loads. Here you can see a street of old masonry buildings, and look, almost every one of the top floors of these buildings has lost its external wall. And that was the pattern right throughout the city. So I think we could say the most extensive failure was for out of plane forces causing collapse of walls, but there was other damage as well. Here's another street, and wherever the walls were not tied well to the floors and the roofs, there we experienced this face load collapse. The rest of the building, in this case, is relatively undamaged. Here is quite a severe case of the upper walls being lost. There might have been some load-bearing timber framing within the building, and so that's prevented total collapse. But you can see how the thick facade has fallen away from the main structure, and it's left this failure line going right down to the foundation here. You can also see that the loss of the facade wall, excuse me, I'll just annotate with my mouse. You can see that the loss of the facade wall hasn't affected the load bearing of the floors. And that's because the floor structure is spanning parallel to the facade. And so at least the building didn't totally collapse because of the direction of the floor spanning inside the building. As I mentioned, it was very common for gables to collapse. And here is a close-up example where all the bricks, most of the bricks of this gable have fallen. And what we can observe is that there was no strong connections between the masonry and the timber roof framing. And so effectively, these bricks were just like cantilevering under face loads. And of course, we can actually tell that the masonry is not in at all good condition. Some of these bricks are really loose, and you can see that some mortar has been lost. So the masonry the mortar wasn't very good quality, and so under even small face loads, such gable walls as these are just can almost be expected to fail. And even when the masonry was bolted back to the roof framing, we found that the workmanship often was not very good. And so these are bolts that have been retrieved from the masonry after the earthquake. And so here's an example, excuse me, of a bolt that was anchored into the masonry using epoxy grout. But during the earthquake, the bond between the epoxy and the masonry was affected by probably the dust caused by the drilling of the hole. And so the epoxy grout didn't bond to the masonry in this particular building. And so the masonry just fell away from these bolts, which unfortunately proved to be useless. And these bolts had been installed as part of a retrofitting program, maybe a few years before the earthquake. So this was just a reminder to us that when we do retrofit, we've got to make sure that the quality of construction, is very high. Otherwise, the earthquake will discover these points of weakness, and we will end up with performance perhaps almost as bad as if we had not retrofitted that building. Another example of face load collapse. This wall is just on the brink of falling. In fact, I think it's probably been restrained by the roof of the neighboring building. And so we have to be very conscious actually of neighboring buildings, because if a masonry building has not been retrofitted, then actually is putting its neighbors at risk. Now, most of my slides so far have showed examples of face load collapse, but I want to just point out that there were also many examples of buildings failing in shear. And so this is in plane failure, and these diagonal cracks in the piers of this building, they speak very clearly of in-plane shear failure. And so this building at each level has really suffered very badly from the overall inertia forces being resisted by this front facade. And the level of those forces were high enough to cause shear failure in the masonry within these columns or piers. Here is another building with large openings at each level. And in this case, although we did get a little bit of cracking in the piers, not a lot, we mainly got a failure in the spandrel beams. These are masonry. And so due to the distortion of the building, we get high shear forces in the spandrels, and where they are the weakest, in this case at mid-span, then we get failure occurring at every spandrel. And this pattern continued up the building too. The highest spandrel panels also totally failing. And at the top of the building, it looks as if we got a bending failure at the base of these upper piers here. And so we get shear failure in the spandrels and some bending failure of the piers. And so this type of damage was relatively common where we had buildings with many openings. You might say when the designers had basically created a frame building using unreinforced masonry. We know now that this doesn't work. Masonry is far too weak a material to be used as a moment frame. Before I go any further, I'll just mention that after my presentation, there will be time for questions and discussion. So please just jot down any questions or thoughts that you'd like to share, and we can address those at the end of the presentation. So now I want to move on to the next part of the presentation, where we just look at the way the forces should be moving through a masonry building. And by understanding the way the forces move, the force paths, then we can appreciate perhaps what's required when it comes to retrofitting a masonry building. And so these are the considerations that are necessary. We first of all got to think about, I beg your pardon, the source of the inertia loads of the building. In other words, we've got to think about where the weight of the building is, because wherever there is weight or mass in an earthquake, we would have inertia forces. We've got to pay particular attention to face-loaded walls in order to prevent the types of failure we saw in Christchurch. We've got to give very careful consideration to the way we support our floor diaphragms and the way they are connected to the walls to prevent face load failure. Then we have to think about walls that are loaded in plane and will experience bending moments and shear forces. And finally, we need to think about the foundations. You know, are the foundations strong enough to support the earthquake forces that will be moving through them and to them? And so we're going to look at a little simple masonry building, which actually would have been quite typical of those shop buildings in Christchurch. So the common scenario is to have shops at ground level, and then perhaps professional offices or even accommodation at the higher levels. And there are lots of these types of buildings in my own city of Wellington, actually, although most of them now have been retrofitted. But we're going to look at this unreinforced masonry building and just look at some of the principles of retrofit. So just as an overview, we can see that we've got very much an open facade at the street front, and that immediately would cause us to be concerned. And so that means that at least for the front of the building and for earthquake shaking parallel to the street, there's a chance of very severe damage to the masonry at this end of the building. And then we can see in the direction at right angles to the street, we can see actually we've got three really solid and long walls. And so it's going to be very unlikely that this building is going to get severely damaged in this direction, because these walls are so long and probably quite strong. However, these same walls are likely to suffer damage in the event of them experiencing face loads, because they're so high, such a large area, such heavy weight in the masonry, and so we're going to have to attend to securing these walls for face loading. So we just now can look at one of those long walls in elevation. We can see that they extend pretty much to the whole height of the building. And then at each of the floor levels, we can see where we have the potential to create a floor diaphragm. Now, a floor diaphragm is a floor slab or a floor structure that in day-to-day usage resists the gravity forces on the flooring and the weight of the flooring itself. But during an earthquake, that floor system, it suddenly becomes a diaphragm because it has to resist the face loads from the walls and then transfer those face loads into structure, usually at each end of the building. And so if we are retrofitting this building, we've got to apply some form of structure to make the floor slabs function as a diaphragm so they can transfer the forces to the masonry wall at the right, and also to probably a new steel structural frame at the front facade of the building. And so these diaphragms, they will have to be strongly connected to the brick wall to resist the face loads, and then the diaphragms will act as horizontal beams, transferring the loads into this wall and to say this new steel frame at the front of the building. Once the diaphragm forces get into the back wall of the building, they will be transmitted into the masonry through steel members bolted into the brickwork at each level. Then those horizontal shear forces, they will then start to go down the masonry wall through the formation of diagonal compression struts in the masonry. And so at the roof level, there will be horizontal forces from the diaphragm. They will cause these horizontal compression forces moving down towards the foundation. And so at this level here, we need a horizontal steel tie to drag these forces back horizontally to this side of the wall, and then the forces can continue their journey down to the foundation. At the first floor level, we will also need a steel tie to drag the forces back, and then finally they can form these compression struts and go down into the safety of the foundation. These arrows here, they just indicate the way we have to drag those forces back through these horizontal steel ties so the forces can resume and form these compression struts. And so we visualize the movement of the earthquake forces through the masonry by this analogy of a simple vertical truss. Just looking a bit more closely at the connection between the masonry and the floor diaphragm, now we are looking, well, it can be any length of masonry wall, it doesn't really matter which, but anyway, we've got, this is the direction of earthquake shaking. And so in this particular case, during the retrofit process, we have screwed or nailed sheets of plywood to the underside of the floor system. In this case, we've got timber floors. So there'd be hundreds and hundreds of screws nailing the plywood and the sheets to the underside. And then we will have strongly bolted, say, a steel angle section underneath the floor. And this angle will be bolted at regular centers into the masonry, perhaps using epoxy grouted bolts. And then we would have bolts and screws from the steel angle into the plywood diaphragm. So the forces in this direction from the floor system, the floor diaphragm, are transferred through the plywood into the screws and nails that go into the plywood to transfer the forces into the steel angle. And then the steel angle then transfer the forces horizontally along to the end of the wall. And then the bolts into the masonry transfer the forces into the masonry. And then they take the form of these diagonal struts that then start moving down towards the foundation. The other important feature of the steel angle, or it could be another shape of steel cross-section, is that the bolts will prevent the whole wall from failing in face load. And so for earthquake shaking in the direction at right angles to this masonry, these bolts will transfer the load almost immediately into the plywood. And so the floor diaphragm, it plays essential roles in both directions. You know, in one direction, it's transferring inertia forces into this wall. And then for earthquake shaking in the other direction, the diaphragm is supporting this wall against face load. So these connections and the diaphragm, you know, are just so important as part of the force paths and the way they move in a retrofitted masonry building. I mentioned to you that if we had diaphragms at the roof and each floor level, the normal scenario is for the diaphragm to transfer half the inertia load to the back of the building and half of the inertia load to the front of the building. And so now we can see these inertia forces that have been transferred by the floor diaphragm. We can see them acting in plane along the front facade. And as I mentioned earlier on, there is no significant structure to resist these forces. You know, like these piers are just so thin and fragile, and it would be impossible for them to withstand any bending moments or shear forces of any magnitude. And so in a building like this, you know, that would almost be essential to put in a new steel moment frame, new steel columns going right up to the top of the building, and then at each floor level, new steel beams bolted or welded to create rigid connections at each junction between column and beam. I haven't shown you that new steel frame, but we'll come across it quite soon in the next few slides. So there we are. That's just looking at the force paths and the primary considerations we've got to make as we approach the retrofitting of a masonry building. So let me talk about several different approaches to retrofitting. And so the first approach I'd like to discuss is how we can improve the seismic performance of what we have already in the building. So, you know, if possible, we try and work with the existing strength of the building. And in the first instance, we try and see if we can improve what we've already got, you know, before we come in with more disturbing structural interventions. And so just as an example of the way we could improve the performance of an existing building without adding any new structure, I'm just taking this case study of a corner building. Like, imagine this building. You can see the section, the plan view. Imagine this building is on the corner of a block of buildings, and so we would have a street running along this line here and a street up here. And so along the street frontages, there is openness, relative openness for retail. But then on the other two sides of the building that would be adjacent to neighboring buildings, because this is an urban situation, these would be masonry walls, there for fire protection. Okay, so these would be solid walls. And so from an earthquake point of view, we have a very undesirable situation where the center of mass of the building is pretty much in the plan of the building. I mean, it'll be a little bit over here because of the extra weight of these two walls. But the center of resistance of this building, that is way over to the left-hand side here, because we've got so much strength on this line and so much strength on the line in the y direction, and not a lot of strength elsewhere in the building. And so that means that during an earthquake, the building is going to twist quite severely. And as it twists, there's going to be extra damage put on these columns near the corner. And so one way of improving the performance of this building would be to use saws and to make cuts in the masonry wall. And if we use these saws and put cuts in the wall, and of course we have to fill the cuts with fire resisting sealant, something that's flexible. By putting lots of cuts in these two walls, we are weakening the wall incredibly. And so now these two walls are far, far weaker. And it means that the center of resistance, you know, moves a lot closer to the center of mass. And therefore, there's going to be far less twisting of the building in an earthquake. And therefore, you know, we've significantly improved the earthquake performance of this building, not by adding any new structure, but actually by softening some of the existing structure. And so as engineers and architects, you know, we need to work together to identify what are the strengths of an existing building, and see if we can use those strengths. And occasionally we have to weaken those strengths. And by so doing, we might get a far better earthquake performance out of the building. Another example of where we can make use of the existing strength is in this building, which I showed you earlier, really. It's like a shop building, open along the front of the street. And then we have these long and usually strong unreinforced masonry walls. Now, if the building is quite long in the Y direction, it may not be possible to strengthen the diaphragms enough to transfer the loads just to the back of the building and to the front. And so in cases like this, we might put in a series of new moment frames. And the purpose of these moment frames is purely to provide earthquake resistance in the X direction. And so rather than having one huge moment frame at the front of the building and making the diaphragm very, very strong, what I'm suggesting here is to put in, I don't know, 4 or 5 smaller moment frames, pretty much equally spaced along the length of the plan. And so that these new moment frames, you can see the columns in plan. I mean, I'm using structural steel because that's easy to prefabricate and it reduces the on-site labor and intervention. And so here you can see the steel columns. We may have to strengthen and put in some new foundation pads at foundation level. That's very possible. We'd have to do that. And then these dotted lines, they show the new beams of the moment frames. And so in this building, we are actually putting in new structure in the X direction, but we probably don't need to do much in the Y direction. We probably can keep the unreinforced masonry wall to resist the earthquake shaking forces in the Y direction. However, we will definitely have to make sure that we provide enough face load resistance to the masonry wall. And in that regard, if we tie the masonry wall to these columns and maybe to a new steel member at each floor level, then that may be all we need to do to give face load support to this masonry wall. And finally, at the back of the building, in order to avoid torsion, we might choose to soften the unreinforced masonry building here with saw cuts so that it is not a strong, stiff element and it won't cause torsion, but rather we will now resist forces at the back of the building on the new steel portal frame or steel moment frame here. So here's an example where we are putting in new structure, but only in one direction, basically, and using the existing strength of the masonry walls in the other direction. Quite often, though, we find that the masonry quality is so poor, or that the length of the masonry walls is so short, that we've got no option but to put in new structural systems. And so it's relatively common that we might create new reinforced concrete shear walls. We might cast these walls between existing columns, and we would need the reinforcement steel in the walls to be continuous up the height of the building. And we would also need horizontal bars, grouted into existing masonry piers or poorly reinforced columns that are existing. So, it's quite common for us to create new shear walls that will resist the earthquake forces in one or both directions of a building. Steel braced frames are also very common, at least in New Zealand and in other countries like United States, especially on the West Coast. And so it's very common to have steel cross brace frames that are designed to support the entire earthquake forces of the building, and therefore, provide a building that is going to perform relatively well. Another approach we will often try and take in a building is to reduce its weight. I mean, I find it quite funny really, because, the medical profession, probably internationally, is always reminding us adults that it's not good for our health to carry too much weight. And we're being encouraged, to reduce our weights. Well, exactly the same principle when it comes to unreinforced masonry buildings. The more we can reduce the weight of a building when we are retrofitting it, the less structural intervention is required. And so the most obvious place to reduce weight is to remove any masonry partition walls in a building. So, if you've got masonry partition walls, then it's really a great idea to remove them and replace them with light timber or steel framing with plasterboard linings. And thereby we greatly reduce the weight of the building, and it just makes it a lot easier and also cheaper to provide new resistant structure. Then just a brief note on how to avoid pounding. Usually when we look at a street of masonry buildings, we discover that there is no separation gap between each individual building. The buildings are usually built against each other, and I mean sometimes they will share a load-bearing wall or a boundary wall between them. And so occasionally, in cases like this, it's possible to tie the buildings together to prevent them pounding in an earthquake. And so one option that we should at least consider is to tie the buildings together so they move as one entity. And so here we've got two shop buildings side by side. This is where they meet each other. They're possibly not structurally joined, but the walls are built against one another. And so in a case like this, what we could do is we could put new moment frames into just one building and then tie through to the second building. And so it would mean that the intervention on the second building, could be relatively quite minor compared to what we did on the left-hand building. And I mean, this would assume, I guess, that these two buildings are owned by the same building owner. And then if they wanted to, they could create openings, I suppose, and make it one larger shop. Alternatively, what we could do is, like in the Y direction here, we could put in some new shear walls, in this case, strengthening each building in the Y direction. This is assuming that the masonry walls are of very, very poor quality, so they're not strong enough to resist forces in the Y direction. So we would put in 2 new shear walls in each of these buildings. But once again, we might just choose to put our moment frames into one building and tie through. And so by tying our buildings together, it means that they're not going to be pounding each other. They're going to be moving together in the earthquake, and there's going to be a considerable reduction in damage during the earthquake shaking. So there are just a few brief principles about retrofitting. Now I'd just like to share some examples with you. And first of all, an example of exterior structure added to a building just to stop the masonry wall failing in face load. So in this case, the designers decided to put some vertical steel members on the outside of the building, probably because it was cheaper and easier, and they had access. And so this is like a vertical steel stud, or you could say a vertical steel post. But actually its real intention is to be like a vertical beam. And so it is strongly anchored into the roof diaphragm at this level here and down below. And then, I don't know, at every 600 millimeters or every meter, there will be bolts bolted into the masonry so that under face load, the inertia forces from the weight of this masonry will be transferred through the bolts into the steel beam or post, and then the steel beam will bend and transfer the forces into this diaphragm here at this level, and then half of the forces will go into the diaphragm at the base of these steel members. And so this is a wee bit of an unusual example of putting the face load structure on the outside of the masonry walls. Usually it's more common to put it on the inside. And so here is an old brick masonry wall here. And here you can see the new steel studs or posts that span from the floor diaphragm here up to the floor or roof diaphragm at the top. And then at these regular centers, we grab hold of the brick through these steel cleats and bolts, anchoring back into the masonry. And so with this vertical structure here, we've now provided this wall, with very, very good face load resistance. There's no way this wall is going to even get severely damaged during a large earthquake. In this, excuse me, in this building, we can see the designers have inserted at least one new steel moment frame. The steel section is orientated, so it's strong in the direction at right angles to the wall. And so here's a universal steel column, a universal steel beam. And this is probably at the roof level, it's ceiling level. And so this is a rigid joint, creating that rigidity that we need for every moment frame. Excuse me. Here is a horizontal steel tie. You can see how it's anchored back into the masonry at frequent centers. And so this member will help with the in-plane forces in this wall. And this member will also help with out-of-plane forces as well, and transfer them to the moment frames that run along the building. Here is a gymnasium structure built of unreinforced masonry. And we can see the way the designers have designed and constructed a whole new roof diaphragm for this building. And so the roof diaphragm takes the shape of a horizontal truss. You know, you can see the diagonals. And so in plan, this is nothing other than a horizontal truss. And it's designed to collect the inertia forces from the masonry. They'll be picked up by members on the outside of the wall and this horizontal member. The inertia forces on this part of the wall will be transferred through this member into the truss, and then the truss will then work as a horizontal beam and transfer the forces to each end of the gymnasium. And I'm just wondering if this might be like a new reinforced concrete frame at this end of the building, designed to withstand the forces being transferred to it from this cross-brace diaphragm. And so we need strong structure at this end of the gymnasium, and also we need strong structure behind where this image is taken. So in this case, the main intervention has been the design and construction of really quite a significant steel diaphragm. And you can see the way the new steel work is hanging from the existing roof structure of the gymnasium. I mean, this structure itself is not very heavy, and so it's quite likely that the existing roof was able to withstand the weight of this truss. And then I'd like to just bring you to this masonry building in the heart of Wellington. It was a former bank, and in plan it's shaped rather like a triangle. So this is like the point at the end of the triangle, and then the triangle broadens out along the length of the building. And this entire building consisted of unreinforced masonry walls and timber floors and a timber roof. I'll just go back. So the first step in the retrofit of this building was to put in some supports to support the weight of the masonry walls, and then to cut a slot right along the base of the building. And so first of all, some holes were drilled and circular steel beams were put in to support the weight of all the masonry walls and piers. a new reinforced concrete wall was built in the basement of the building. The existing cast iron or maybe even steel columns were cut, and they had their loads supported on temporary formwork, while new foundation pads were installed. And then in the basement, some new reinforced concrete columns were placed, and on top of each column was placed a lead rubber base isolated bearing. And so the primary means of retrofitting this building was to base isolate it. A very complex and expensive process, but this method achieved the designers maintaining as much of the historic fabric of the building as possible. And so the interior columns are all placed on these seismic isolators. And these same isolators, they were put in the slots all around the existing perimeter as well. So there were tens of these bearings put around the perimeter and under each of the internal load-bearing columns. And then it was necessary to upgrade the strength of the timber diaphragms, the timber floors. And so first of all, some new steel members were bolted internally along the length of the building. And then on this particular floor, new steel strap bracing was fixed to these steel members and then attached to them. And so these steel straps form another horizontal truss at this floor level, enabling the inertial forces from the walls to be transferred to each end of the building. So there's going to be maybe some new steel bracing put at this end of the building and the same at the other end of the building. Because this building is seismically isolated, it means that the inertia forces that it will experience will be far less than for a non-isolated building. And then at roof level, another diaphragm is constructed. And this time, the designers chose to use plywood to upgrade the ceiling diaphragm. And so here you can see the sheets of plywood set out in the staggered pattern. And although we can't see it, there would be thousands and thousands of nails, running around the perimeter, each of these sheets, to create a really strong diaphragm. And this diaphragm, it will connect to new steel members running along the length and across above the new structure in the transverse direction. I mentioned early in the presentation about using reinforced concrete shear walls as a means of retrofitting. Well, here's an example of using reinforced concrete, but actually spraying the concrete in. This technique is called shotcrete. And we begin by placing the reinforcing bars for the shear wall into position and bolting them into the existing masonry behind them. We've got to remove the plaster off the existing masonry so the concrete will bond, really strongly with the brickwork. And then we have a very special concrete mix that is propelled with compressed air and sprayed against the existing wall. We usually provide some wire netting on the front face just to prevent the wet concrete from like falling off the wall during the spraying process. So it's quite a tricky process, but of course the people who do this work become quite experienced, and we can end up with, you know, a very effective way of achieving new reinforced concrete shear walls. Here is an old masonry and sort of an unreinforced concrete building, which was lacking seismic resistance in both directions actually. But like in this longitudinal direction, some of the existing fabric of the building was demolished and new eccentrically braced steel frames are inserted. And so in this image, you can see 3 bays with new steel framing. And this framing goes up the 3 stories of the building. And I think they might have even built some extra new stories on top of the building at the same time to maximize the financial, you know, benefit. And so now in the longitudinal direction, the earthquake forces are now resisted by these really strong and ductile eccentrically braced steel frames. This is the area where we have the eccentricity between the brace members, and this is what we call a structural fuse. In a large earthquake, this region will be very severely distorted. It'll absorb a large amount of earthquake energy and essentially protect the rest of the steel members from failure. From memory, this building also needed new structure in the other direction as well, but I just can't show you that in this particular slide. Here's another example of new steel structure being applied to an old building of concrete and masonry. And so on the back of this building, where there was access, you can see how the designers have built and attached a whole new steel moment frame. And so here is a rigid joint. Here is the bolted connection where they did an on-site connection, you know, connecting this part of the frame to this part. And I think here is probably where they joined the columns at mid-height. Once again, this would be, it might have been a welded connection. And in all these steel members, although we can't see it very clearly, they need to be bolted with hundreds of bolts so that their forces from the existing building can be transferred into this new structure down to the safety of the foundations. At the front of the building, they built a similar frame like this inside the external facade. And so they had to do quite a lot of local demolition to put the new steel frame inside the building and then bolt that to the existing structure. And so another example really of new steel framing being used to provide, you know, a new structural system that is able to withstand earthquake forces and perform well. So those are just a few examples of retrofitting. And so now to close my presentation, I just want to talk about some resources that are available for you if you are interested in pursuing a retrofitting project. And I think probably the most up-to-date retrofitting resources are actually published in this New Zealand government website, published only, 4 years ago. And these guidelines, which you can just download free online, they consist on information on how to retrofit any type of material. But the C8 document just deals solely with unreinforced masonry. And so the contents of this is it looks at typical building practices of unreinforced masonry buildings in New Zealand. It talks about how they've performed in previous earthquakes and what the factors are that affect their seismic performance. It then talks about how we should assess the strength of these buildings, whether or not we need to do on-site investigations. Do we have to do some demolition to establish the strength of the brick and the mortar? Information about the weight of the materials and the likely strengths of members, the overall strength of the building and how it might deal with the earthquake forces and displacements that occur during an earthquake. And then it suggests different methods of retrofitting. And I'm just going to give you a taste of the material because, take unreinforced masonry chimneys. They are the most vulnerable of all the elements of a unreinforced masonry building. Chimneys are the first elements usually to crack and topple and fall. And so here are some techniques to retrofit them. We can do internal post-tensioning. We can put in some internal steel tubes. We can fill them with concrete and reinforcement, or we can put external steel strapping. What about walls? For face-loaded walls, we could put vertical timber or steel mullions or studs or posts. We could put in horizontal members that span horizontally between, say, new moment frames or new shear walls. We could do internal post-tensioning of exterior masonry walls to improve their face load resistance. We could do external post-tensioning. We could put in some internal bonded reinforcement, or we could put some composite fiber overlay, like plastering, especially internal walls, with layers of reinforced plaster to give face load resistance to those walls. When it comes to connection of the walls to the diaphragms, once again, a number of different techniques are provided. And then when it comes to strengthening masonry walls for in-plane forces, in other words, to prevent those very serious diagonal shear cracks, and also to prevent the bending failure of masonry piers, here are a whole lot of other techniques that can be used by designers. And so, this is a real toolkit of options for you. And then if you want to further investigate and look at a very accessible document, I'd recommend this tutorial written by Jitendra Bothara and your own Svetlana, a tutorial improving the seismic performance of stone masonry buildings. And so if you're working more in stone masonry rather than, say, brick construction, then it would be worth you just having a look at this publication that is also a free download from the World Housing Encyclopedia. And in your notes, you can just work out how to get hold of that document. And so just to conclude my presentation, a couple of thoughts primarily aimed at the architects among you. And that is that retrofitting should, well, hopefully always respect the existing architecture. What we so often find in seismic zones is retrofitting does not respect the architecture. It is just placed there, is probably designed by engineers without any involvement of architects. And the engineers are doing the cheapest job possible. And probably that job could be, look horrible. And here's, for example, a building in San Francisco that has been retrofitted. And see the diagonal brace that is forming a braced frame up the building. Here's the brace at the next floor above. And I mean, this is just a disaster in terms of the architecture, isn't it? I mean, this is just so crude, having this diagonal brace cutting through the entrance to this building. The brace, it destroys really the existing orthogonality, you know, of the columns and beams of this building. And so, unfortunately, cross-brace frames are probably the most cost-effective means of retrofitting. But please, engineers, be mindful that they may have a huge adverse impact on the architecture. On the other end of that continuum, here is an old brick building, a lovely old brick building in Wellington that I and a couple of colleagues did a strengthening scheme for a few years ago, purely an academic exercise. And in this building, we strengthened it using shear walls created from steel plates, where we laser cut, we intended to laser cut the plates into this pattern. And so actually we were creating new steel shear wall panels, basically made up of these tension diagonals that were to provide the new face load and in-plane resistance to this brick building. And so in this scheme, we were trying to use the retrofitting structure to enhance the existing architectural qualities of this building. These panels were all to be applied on the inside surfaces of the brick walls. And so this was an attempt to not only avoid destroying the existing architecture, but actually to try and add another layer of richness to the existing architecture. And so, you know, this was just one of the schemes that we came up with in this little research project we did. So on that note, I'd just like to thank you for your attention and hand you over to our chairperson, and presumably there'll be opportunity for questions. Thank you. I'm just going to try and stop sharing.
Thank you very much, Andrew. I believe that I cannot see Rade that is on the call. Maybe again he has problems with the internet, so I could coordinate the questions if there are questions for sure. Thank you very much. It was a very interesting presentation. I do have a question, but I would like to invite others to ask if they want. They can write in chat or ask. You can also ask in Serbian if that is možda pitate na srpskom ako vam je zgodnije, pa ću ja da prevedem. Hvala puno. Any questions from the colleagues who are present? They are students and they are colleagues from practice as well and from academia. So any questions about this topic? Very interesting way of presenting as well, and the scope content. So I'm not sure if Rade has joined. So anyways, I can ask a question, Andrew. And it is focused on New Zealand. You presented a number of examples from New Zealand, and you have also been in Serbia, and you've seen our buildings and the type of construction we have, and you can now imagine what kind of retrofit we would need. So based on New Zealand experience, what was the most cost-effective retrofit for, let's say, of course, we're talking about masonry buildings, unreinforced masonry buildings. You showed some challenges with the anchors that were revealed during the earthquakes. And in Serbia, we actually don't have I'm trying to ask a question, so it is useful. The answer is applicable to our practice. We have many older unreinforced masonry buildings, but many of them have rigid floors. So if we have that case, and that is unlike what was there in Christchurch in older masonry buildings. So in case of these buildings, what type of retrofit do you think would be most cost effective? And we do have open front buildings. So that is, and I saw that you were looking into so for example, for those buildings, you were focusing a lot on steel solutions, but let's say, what about, let's say in Serbia, we use reinforced concrete. Would that be, do you think that it would be equally effective if we would, solve, let's say, problems or issues related to these buildings with the reinforced concrete? Has it been done in New Zealand? I know steel is widely used, but what about, or alternatives, what I would say, alternatives to steel?
Yeah, okay. Yeah, thanks. That's a good question. Well, first of all, I think the fact that most of your floors in Serbia, I'm talking about like multi-story buildings, the fact that most of your floors are reinforced concrete, that is a very helpful situation, because it means that essentially you've probably got quite good diaphragm behavior because your floors are reinforced concrete. And also because your floors are concrete, it means that at least your load-bearing masonry walls have more compression in them, and that increases their bending and shear performance. So those are two advantages that you have that we don't have in New Zealand. But look, we have used reinforced concrete members for some retrofit projects. I can think of some jobs in Wellington where I can think of quite a few jobs where we've used new reinforced concrete shear walls in one direction, and in the other direction, we have indeed used new reinforced concrete moment frames. So if you've got, a large unreinforced masonry building, say in Belgrade, with an open front facade, yes, by all means, and it depends on your building economics, by all means put in a new cast in place reinforced concrete frame you know, at the front of that building and maybe within it as well. But you could also think of having some of those members of your frame as precast too. You know, it's just something that the designers and the contractor needs to work through together to get the most cost-effective solution. But yes, reinforced concrete framing members are perfectly fine. It's just that with reinforced concrete, you're just adding a bit more weight to your existing building. But I mean, if you're using new moment frames, actually the increase in weight would be, I guess, almost insignificant. And so, yeah, go for it. Use your reinforced concrete.
Thank you for this. Any questions from the audience, from the participants, please feel free to ask. We have some time. We planned for this for 1.5 hours, and I forgot to mention that at the beginning, but that was mentioned in the announcement. So we have a few more minutes based on our schedule. So,
Svetlana, I just need to mention that unfortunately I do have another appointment.
Sure. That's okay.
In about 5 minutes.
Okay. No, sure.
So look, if anybody has a question, I would be happy for them to email me. And okay. Perhaps, Svetlana, you could just let people know what my email address is. Okay. And if someone has an issue or question, look, please email me and I'd be happy to answer it for you in the next few days.
So those participants who are interested in asking a question can send an email to SUZI email address, and we will forward to those who are interested Andrew's email address. So in that case, since you have another appointment, I believe it's good time then to close this event, to thank you for a great lecture. I really enjoyed, and particular examples and the case study very nicely presented. And thank you on behalf of Serbian Association of Earthquake Engineering and Architectural Faculty, the Faculty of Architecture at the University of Belgrade, and all members, participants in this meeting, and others who will watch it after it is posted on the YouTube channel. SUZI has a YouTube channel, and it will be there. So thank you so much, and see you hopefully in Belgrade and virtually or remotely, depending, or physically, hopefully in the future. Thank you, Andrew, and thanks to all participants to attend this late evening session for the first time by SUZI. Actually, this is the latest ever we have done. Thank you, and have a good night and a good morning, depending where you are.
Okay. Goodbye. Best wishes to you all.
Yeah. Bye.